Logistic Regression, Gaussian Discriminant Analysis, Naive Bayes. At first glance, these seem like completely different ways to solve classification problems. Some search for decision boundaries. Others model probability distributions. But all of them are trying to answer the same question. How can a machine decide which class an example belongs to? We've already seen logistic regression. You collect data. You label examples. And the algorithm searches for a boundary that separates one class from another. But then researchers asked a different question. What if instead of trying to separate the classes, we tried to understand them? That's the idea behind generative learning algorithms. Imagine you're a doctor trying to classify tumors. Logistic regression searches for the best boundary between malignant and benign tumors. A generative algorithm does something different. It learns what malignant tumors look like. It learns what benign tumors look like. Then it asks, which class does this patient look more like? Instead of learning a boundary directly, it learns a model of each class. Mathematically, discriminative algorithms learn the probability of a class given the features. Generative algorithms learn the probability of the features given the class. Then use Bayes' rule to work backwards and calculate the probability of the class. This idea leads to Gaussian Discriminant Analysis, or GDA. GDA assumes that the data inside each class follows a Gaussian distribution. Using statistics learned from the training data, it models each class and classifies new examples. If the Gaussian assumption is correct, GDA can perform extremely well, especially when data is limited. But if the assumption is wrong, performance can suffer. This reveals an important lesson. Strong assumptions can help when data is scarce. Weak assumptions can help when data is abundant. But what if the input isn't numbers? What if it's text? Researchers solved this by representing emails as vectors of words. Then they made one bold assumption. Once you know whether an email is spam or not spam, the appearance of each word is independent of every other word. That assumption leads to naive Bayes. Naive Bayes estimates how often words appear in spam and non-spam emails, then uses Bayes' rule to determine which class is more likely. The assumption isn't perfectly true, but it makes the algorithm fast, practical, and surprisingly effective. And that's the key idea. Logistic regression, Gaussian discriminant analysis, naive Bayes. They may look different, but they're all trying to solve the same problem. How do we use data to estimate uncertainty and make better decisions? Some algorithms learn boundaries. Others learn distributions. But they're all different paths toward the same goal. It's about choosing assumptions. But this raises another important question. If our goal really is to find the best possible decision boundary, can we do better than logistic regression? Can we find a boundary that not only separates classes, but separates them with the maximum possible margin? That question led to one of the most influential classification algorithms ever created: support vector machines. And that's exactly what we'll explore in the next video.